Is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to today's webinar. Our webinar today is going to be about OSLO and kind of introducing folks to OSLO and some of its capabilities. The presenter for today is going to be Dr. Richard Youngworth. Dr. Youngworth has his PhD from the Institute of Optics at the University of Rochester and has worked in the optics industry for over 25 years now. He works with Lambda Research Corporation, ourselves here, in our application engineering and development teams, along with running his own company, Rio LLC. He also teaches a successful SPIE short course on practical optical system design. If anybody's interested in that, it's SC003 at the SPIE conferences. He's a fellow at the SPIE and also an adjunct associate professor of optical sciences at the University of Arizona. Before I turn it over to Dr. Youngworth here, just a couple quick notes on today's webinar. One is we are recording this webinar, so the archive copy will be available probably within the next day or so on our website for download. Also, there is a question or a chat box available. So if you are able to, if you have any questions during the webinar, please feel free to type those questions in and you'll be able to, we'll address the questions at the end. And again, any questions we don't get to at the end, and I'll remind folks that at that point, we'll try to address via email. So with that, I'm going to turn it over to Dr. Richard Youngworth for today's presentation. It's all yours, Richie.
Great, thanks. Hello, everyone. So I'm going to start with just a few slides, but we're going to spend most of our time in the actual program. OSLO is an easy-to-use, powerful, and flexible tool. It's been my go-to program for many, many years. It has a very good history. It was the first of these types of programs to show that you could do serious optical design and engineering on a desktop computer. It, in the past, has been used to benchmark other ray trace codes. It's got a great record for accuracy and success in many different markets, and I'll show some examples on that. And it's a primary optical design and engineering tool that's been used for a lot of cost-effective design and manufacture. It's really easy to find on our Lambda research site. So just a little summary of kind of high-level summary of what it does. Lens design and analysis. It's got very good optimization and tolerancing tools, many different ray tracing options that can be quite efficient on how the ray aiming is done, quite advanced. It has non-sequential capability. At some point in the webinar, it's certainly worth saying it's not an illumination and stray light program. For that, we would certainly refer you to our program TracePro. It has incredible flexibility, which has been one of the primary reasons I've used it for so long. It has a macro mode, which goes back the longest, but it actually has a fully compiled internal programming language. And often people call CCLs macros, but they're actually compiled. So they run faster and extend the capability of, beyond what normally macros can do. And the data inside of the program is easy to access, export, and you can also build DLLs. So it can do quite a lot. So let's go into the program a little bit. I've got just a double Gauss type lens. It's not completely optimized here. Normally, I would actually have my windows set up a little differently, but I'm on a little laptop for this presentation, so it's not quite the way I would necessarily set it up. You can open many, many windows, up to 32 for graphics, so you can have 2 text windows open. The primary way that OSLO works is according to a number of spreadsheets. There are other programs that have followed this type of template. And so look here, this is the main lens spreadsheet editor. So this is where a lot of the work is done. One thing about OSLO is the way it's set up is there's a little bit of layering in here on how different things can be accessed, which might be a little bit different from other tools that people have used. And so you have to get a little bit used to a few interface design choices that have been made in OSLO. I find that most of our users, when they first start, they may take a little adjustment period, but there's a lot of strengths and power in what we've actually set up and how it works. And there's some differences with Windows, but I've found that most users can be flying through the interface with some of the advantages pretty quickly. So one of the things, we have a whole video, we have a lot of videos online to help people learn how to use the program right now. I think we're up to almost 40 training videos. And one of the things is this check mark and X. You might want to look at it. When you see me hit the check mark, I'll be accepting changes that were made, and if I hit the X, I'm rejecting them. This little question mark down here just opens up the help. So that's a really key thing to know about. And the really nice part about this help, if I click on some other button, for example, and I hit the question mark, it'll pull up the help for that very page. Just an awesome feature. Really easy to find things in the online help. In addition to our online help, we also have an optics reference book published and a program reference book published, and a lot of very good information in those. So there's quite a bit of documentation behind the program, and that's one easy way to get to it, certainly the help. The other thing that you'll see is beyond these spreadsheets that you can open up that do different functionality, the graphics windows and text window down here, they have reconfigurability. So you can put different options up, and you can have them different for different windows and open up many different windows. So I find that to be extremely, extremely flexible in terms of how you might choose to use the program. We also have things in the menu up here, and these menus, again, it takes a little bit of time perhaps when you're first using the program to figure out where everything is. When you have a program that many things as OSLO does, you also have to be a little bit careful about remembering where some things are, because sometimes it could be in two possible places. Often we have things that might have multiple places where we can run them. You can run it from a menu, there's a command line, or you can run it from the text windows. The flexibility in how you want to run the program is really quite amazingly flexible and useful. One of the real positive features of OSLO is the fact that it has this command line that's built right into it. And so this command line is incredibly useful because I can use it, for example, if I run this particular command for the refractive indices, this gives all the refractive indices, and it may not have actually tracked it in this case. It actually did. There's a history buffer here, and the history buffer helps you learn some of the commands if you do want to run that way. You can run OSLO without commands at all. You can learn a few that you think make your life a little bit more useful. If you don't know about commands, there's ways to set the program up so the commands will echo through the interface by changing a preference called echo. There are also settings you can use on each specific lens operating conditions. So OSLO has some things that can globally affect every lens you open up in it or every file you open up, and it also has things that affect specific lenses. Now, it seems like a lot, and I know I'm kind of going through this, of course, really fast, but you can learn bits and pieces, and to get to the main functionality only takes a couple of hours. So it's actually quite easy to use and flexible between the help system and the ability to echo commands and the history buffer and just the number of options and ways that we have. And if you watch some of our training videos, sometimes I will show 2 or 3 different ways to get to some sort of an answer or to achieve something. So there's a lot of reconfigurability and other options. The other thing, this is a real massive positive thing in the program. I'm going to actually just take a look here at lens numbers. Every number that's dumped into the text window has a spreadsheet cell associated with it. And it turns out this calculator up here this command line can be used as a calculator. So I can take something, and let's say we take 2 and we use star to the power of 2 to the 8th power, that's 256. So what you can actually do is some crazy things that are easy to do. Let's say I want to make this 25% bigger. I could take cell A18 and multiply by 1.25, and at that point, I believe, yes, that would be 43.5, but you can actually assign it to that cell. So this, when you get used to using that, makes it really easy to do calculations right in the program. You don't have to have a calculator there. You don't need to type in a bunch of numbers. And I have just found this is such a huge time saver and one of the real advantages of our interface, one of the really, really good things. Another nice thing that you can do in here is, let's say I have a command and I don't know additional factors with it. I can use this question mark and it gives me options now. So let's say I just did the refractive indices and it did it for all the lenses. Now, for those of us that have used these programs a lot, they love to spit enormous amounts of numbers out at you. Let's say I don't want that. I only want to look at, let's say, surface 3 through surface 5. You can adjust what it spits out to you, and if you end up writing your own little routines, you can take that into account. So you can make really compact output that's quite flexible. And I have found in my experience, I've used 4 or 5 different programs like this. This has been the most flexible and useful in those types of ways, and I just absolutely love it. So I talked a little bit about commands and this sort of functionality. You don't really need to use commands if you don't want to. So the next thing that I want to move to is showing some things that are calculation oriented. So for example, here, this is just an old sort of 35mm double Gauss type of lens, a workhorse lens that was used for a long time in the industry and still has some applications. If I go here to setup, let's say I want to take this and let's say our sensor is actually a little bit bigger than this 18.19. Let's say I want to make it 20. I can just change it to 20 and it automatically has adjusted the field angle. So it does some first order calculations really quickly and easily, and you could do that for the speed of the lens or the field of view. So it does first order calculations for a majority of cases just incredibly well. I'm not going to show how to do this. There you saw I hit the red X, so I X'd out. Maybe I'll see if I can do it here now. Another thing you can do that's really easy in here is you can actually scale a lens, and it's really useful to be able to scale to new focal length or scale by constants, because sometimes you enter in something from a patent, optimize it a little bit. You might want to scale it to some other number, and you could do that very easily. It's got other little useful things like reversing numbers and being able to copy spreadsheets, copy lines and paste them in and all sorts of things like that. You can also open OSLO files inside of a text editor, and it's just a list of commands. And sometimes that's useful if you get a little bit used to what you're looking at, so you can copy something that you want common in multiple files. So it's pretty easy to do a lot of those types of things. In terms of main functions beyond setting up systems, it certainly does optimization. There's ways to set up some automated setup of different merit functions. Certainly you can set up many different variables. It's very good with zoom and multi-configuration lenses with that. Let me just show here I usually do commands, and every now and then, and if you watch the training videos, I'll do this. I'll type a command in because it's easier for me. So this is actually the operand spreadsheet for this particular system. It's just a optical path length wavefront oriented optimization that has already been set up. If you're saying, well, how do you control something like the focal length? What I've done here is I put some solves in. This is a paraxial image solve. You can use the last surface to do a defocus from that, for example. This one right here is set up with a little solve that is actually going to control the focal length. And if you don't do that, anybody who's forgotten to do that in a lens, lenses tend to like less and less power, so longer and longer focal length. So you usually put constraints on those things. And there's a lot of different ways to do those constraints. You can do them in your optimizations inside of the optimizer, the operands, or you can constrain them in the program like I've done in this case. So lots of different ways to do that. A lot of flexibility there. In terms of variables, in this case, I've got some curvature set up, and of course, it gives you access, and it gives you access in a way that almost seems crazy when you're first using it, because when you use something like damp least squares, it sets up some damping factors. You can choose to even turn those off and allow it to do different things. We've had some users that have taken advantage of that degree of flexibility in order to find new design forms. So it's really, really good at things like that if you're careful about making sure where you start and where you end, and if that's what you really wanted to do, the typical kinds of work that optical designers are going to do. There's an enormous number of analysis options that you can see through the graphics window here for many, many different types of metrics. And additionally, we have a lot of those here in the menu. The tolerancing tools are quite good. It does have some wavefront differential capability, which is the Hopkins-Tiziani followed on by Chuck Rimmer's work. So it's quite good at different tolerancing steps. There are some spreadsheets in here that work on different sort of tolerancing factors. Right now, this one hasn't had numbers assigned, so it's set up to some old ISO 10110 default types of numbers. So, and I could show, you know, for example, you can run, this would be an inverse sensitivity analysis, and it likes to give out lots of numbers, but we have a lot of flexibility. It's reasonable for me to show this at this point. Often when you pull up one of our menus here, or one of our options here, you can see the number of different options that you have. And this is fairly typical when you're not running a command, that if you're using the user interface, this is kind of the way that we can interact with it and how that works pretty well. Okay, just looking through my sheet here. I think we're up to showing a little bit about flexibility. So it turns out in the program, I'm just here, I right-clicked, and now I'm just going to go ahead and clear that window for the moment. There's a lot of flexibility given to you that I've shown through the architecture of the program. One thing I haven't shown yet is the actual sort of CCL. So here's a little CCL that we'll run at the end. It's just going to print thank you for your attention in the window, and it's going to do something in the first window with the wavefront map. And this, as you can see, this is a fairly typical kind of little structure that I do, where I put a comment at the top or something saying what it is. And it follows, largely follows, not completely, but follows a lot of C syntax, but it doesn't have pointers. So the analogy I make with this is, if you've heard or used programs like Python, I don't think CCL is any harder to use than something like Python. And as a matter of fact, when I finished graduate school and I looked at all the tools, I had used Mathematica and OSLO, and I'd used OSLO to write my own C-based programs to do a lot of things that had often nothing to do with optics, because it comes with this built-in programming language. It's quite amazing and flexible for that. But again, you could ask, do I need to be a programmer to use OSLO? No, you don't. The user interface works great. There's lots of ways to do things. It's just we have all this amazing extra capability, certainly enabled by having our command line here with the history buffer, and also all these nice spreadsheet cells that we can use to access some data. Okay, so let's now do some example work. So this is this double Gauss lens. It's actually not quite optimized at the moment. So I actually just wanted to show an optimization. As I said, the curvatures were set up, and we have a wavefront based type of merit function ready to go. So this iterate would run damp least squares. You can also run it from the optimize up here. It also has some downhill or local optimization methods built into it, as well as some global methods built into it, which is important for a lot of users to find different design forms. So here, if I run this, you can see the merit function started off and it was 0.113, and you can see it's now actually been improved. Now, there's a design choice in this, and I've always found that you're kind of in a position where you have a lot of choices of how to do this. OSLO doesn't actually update the windows automatically. We've had some users that have voiced some concern over this. It's actually very easy to update all the windows at once, which I will do a number of times with this command UDA, which stands for update all. It's a really convenient, useful one. But to update a window, all you have to do is double click on it. And our, RMS wavefront errors, when I don't know if they were something like 3, and now they've dropped down to 1.6. So pay careful attention to the ray fans here, and you can see that it's in better focus and has been improved. I could have also just typed UDA and updated all of them. So one way you might want to operate is you keep 2 windows open, you have your metrics you're looking at in one, you do your optimization, so you only update one of the 2 windows so you can compare the 2 side by side. Easily functional to do that, maybe a little different than some other programs where you put a freeze on a window or something like that. Okay, so I'm going to show a number of different examples just to show you how the program works. I've actually updated this. So let me see if this, I'm going to undo all the changes. So I would be back to my original form. That just makes it easier to open. So I'm going to go to a wide angle system, and I'm just going to do my update all. And so you can see this is a wide angle fisheye lens. OSLO has a lot of ray aiming capability. It can very much handle this type of system that has a very extreme sort of field of view, as you can see, which is why I picked this particular example to show. And people have designed very wide angle systems in the program. The next one I'm going to show is just the Hubble. And you say, well, that's a really old system, but it's a reflective system with a central obscuration, which OSLO handles very, very nicely. Here, I'm showing the wavefront maps for it. The other thing is, even if you have metering structures, you can use the apertures to control that. And OSLO has even been used to model JWST. And for a while, James Webb Space Telescope, a lot of the baseline models were being done in OSLO because of its aperture capability to be able to draw these segmented mirrors and some things like that. So the next one, just to show, is a David Schaefer design, which is mirrors. This time I'm just going to double click, and I can update all my windows. So this is a Schaefer design with 5 mirrors, and if you've ever enjoyed seeing some of David Schaefer's work, he has a number of papers where he likes to bounce light off multiple mirrors and correct all these orders of aberrations and these just sort of amazing types of aberration-oriented arguments that he makes in them. So this shows, and he's done a lot of his work, if not all of his work, over the years using OSLO, as far as I know. So a lot of really nice capabilities shown by this. It's very good at coordinates. A lot of things can be done quite compactly within the program. The next one is just to show some multi-configuration or zoom lens capability written by one of my colleagues that I've worked with a lot, Ellis Patensky. So here, if you click on the zoom button, you can see what's changing for the different zoom positions. You can set up different optimization targets with different zooms. You can have variables set up for different zooms, and you simply have to click on this and you can see the different configurations. And we even have, under one of our options on the graphics window, we even have some zoom routines that were written originally for Mr. Patensky. So and he's done a lot of work for over 20 years in OSLO, including some work for some very high-end cinematography types of systems. So it's been very good at that. The next one we're going to look at is just a rifle scope. So this is a compounded system. I'm going to update all the windows on this one. So this is a compounded system. It's got the eyepiece and the objective lens in it, and it certainly can handle these types of systems as well. If you see things like this, sometimes something might be actually, some of the light might not be getting through at that full field. It might be vignetted or something like that. And that is likely what's happening through the eyepiece in this system. I didn't analyze it too closely. It was just merely to show a compounded system like that. The next one's kind of a fun little one, and it's an Axicon beam expander. And so for this one, I'm actually going to change to our 3D sort of solid drawing. Now, this type of program is actually not like a solid modeling program. It's using mathematics to define the surfaces, but you can still set up systems like this Axicon beam expander. So I just wanted to show an example of something like that. I mentioned non-sequential systems earlier, and to give you an idea of non-sequential, picked out this, I just double click there, picked out something with a dove prism. When you have a system like this, I'm going to just go to the plan view. What happens is it comes in and the rays might hit certain surfaces multiple times. You're not necessarily sure as you go in what surface it's going to hit. And this is the sort of modality of the non-sequential that is the most commonly used within OSLO. It doesn't do a lot of flux ray splitting and a lot of things that I consider to be on the side of the stray light and illumination types of tools, which is why Lambda Research has TracePro as well as OSLO in the product line. But definitely wanted to show you how that works. You define an entrance port, you see where rays come out on an exit port. The next one to show is an A-sphere. My colleague, Mr. Batensky, has been long a user of more extreme A-spheres. This one's starting to get some inflection. There's a number of different A-sphere formulations for this. This is just an old CD pickup lens, and this is actually a spline-based surface. And this example actually goes back long enough that Doug Sinclair was the person who, Dr. Sinclair was the one who actually put this in Oslo, and he and I had a discussion about it at one point. So Oslo was a early adopter of a lot of these spline types of surfaces and some capability, which some users have used to great effect. Next one, just to show a system that's a little bit, this is not, no way a state-of-the-art system for this, but here's a few silica lithographic lens, just as an example. And we have had some users do some pretty high-end systems like this over the years with it. So it's capable of wide field of view. It's also capable of fast lenses and ones with tight distortion requirements and other factors like that. Okay, so lots of examples, could certainly show a lot more things, but we don't want to keep you too late. So Oslo has an open architecture. It's flexible. It has accuracy. It's reliable. We've got strong documentation, great support. I've shown some types of systems. It's not even possible for me to name every type of system that our users have used it on over the years. So I gave a list here of space telescopes, camera lenses, zoom lenses, scanning systems, systems that are anamorphic. You know, there's different power in two different axes. Cinema systems, microscopes, ocular systems like rifle scopes and binoculars, spotting scopes, projection systems, endoscopes. It does have gradient index capability, AR, VR types of systems, photolithographic, mobile phone lenses, defense applications, up through IR capability, laser systems. It's got some Gaussian beam propagation capability, and certainly with nice coordinate systems, you can do some steering type of applications with that. Spectrometers, holographic systems. It's got a lot of capability in diffractive optics and much, much more. So for more info, we'd love to hear from you at sales@lambdaresearch.com. For questions or different things you'd like to know about it. But before I go to that, I'm actually not ending the webinar on the ending webinar slide. We've got one more thing I promised, which here I'm going to run that little CCL that was written. And as promised, I'm going to clear this. So I just do web. End is the name of the command if I can type it incorrectly. So we do that. Thank you for your attention. And this is, as you can see, this is actually a smiley face, which is the wavefront map here. And this only took, to make this smiley face, I believe it took 5 things in the aperture coordinates to do that. It only took 5 or 6 to do that entire thing. So thank you a lot for your attention for the main part of the webinar. And now I'm going to hand it back to Dave for the question and answer.
Okay, thank you, Dr. Youngworth. Excellent webinar. I'd like to remind everybody again that we do have a question and answer panel. So if anybody does have any questions, feel free to type them in at any time. We do have a couple questions here that we can address. And let's start off with, how can I constrain my image size as I optimize a system? Is this something that's possible in Oslo?
Yes, it's possible to do it. There's a number of ways to do that. There's as an actual target, this we're showing. If I open up the operand spreadsheet again, I'm just faster, so I'm not on a good lens to do this. I can do this way. I can open it up here. If you don't remember what the command is, you can open this up, and then you can go to operand. This is taking me a couple clicks to do it. For many years, this is kind of how I did it. There's some faster ways to get to it, but let's say you want to do it paraxially, you can do it with the, for example, the chief ray height, and you can pick the chief ray height would be at the edge of the field of view. There's similar operands and other programs that do that sort of thing. That's one way to do it. Another one, if you go back to that, if you go back to the original lens that I had open, which was the double Gauss lens, when you constrain something like the ray angle here, you're actually constraining things sufficiently to control the EFL and the Gaussian image height, or the image height. You could even do it on a real ray target if you wanted to, and a real ray target would include things like distortion. So that's very possible.
Okay. Another question from the same attendee. Can you show how to change the F number in a system? And can OSLO compute MTF?
Yeah, to change the F number, and I kind of went through this a little bit, you would come in, you can certainly do it manually by changing something like the entrance beam radius. And depending on how you set it up, you might have the, let's say you're doing a microscope or something, you might have the object NA in here, and you could do it that way. That would change the working F number in that case. But excuse me, I hit the general. Here, if we go to setup, it's very simple. You can see you can change the entrance beam radius. But let's say we want to change the working F number of this lens and just make it a little bit faster. So we go to a 1.9, you go lower in the F number, and it's faster. So that's pretty easy. The second half of that was MTF. I didn't really go through MTF too closely, but we do have a through frequency MTF capability. And so I just ran that, and there's a lot of different options. This is not the best system to look at MTF with based on how it's corrected. And you can also do, and we love this, a lot of the people I've worked with, we love the through frequency. This one, I actually haven't necessarily picked one that is going to have really nice through frequency data. Maybe this Hubble will. That's it's not so good off axis, but you can see if you line up all your curves and you can compare to a diffraction limit. So it can do that. And actually also when it calculates this, there's a Fourier-based method, but there's also a direct integration-based method. So there's multiple ways to even calculate that in the program.
Had a quick question, I know, about OSLO EDU. Could you mention that just briefly for the people that might be interested in that?
Yeah, you might be even better to answer that than me. So okay. OSLO EDU, the company, we recently moved away from a model where we had three different versions of OSLO. We've moved purely to OSLO Premium. It just made sense for our users to do that. But we still have a free version called OSLO EDU. I don't actually have it installed on this program, but it's free for anybody to use. There's some of the capability is turned off in it. I think it has maybe 10 surface limitation. Yeah, it's 10 surface. And it's used worldwide for a lot of universities and teaching applications. OSLO's quite set very well in some fundamental optics. So EDU provides a very nice vehicle for people to learn some first order optics or even some third order optics as well. But it's even used by some users to do some basic design work. So if you haven't used it at all, you certainly can download OSLO EDU and have a look at how it runs, but be aware some features are of course turned off in it.
Yeah, I see mention every now and then of OSLO EDU from amateur telescope makers as well, looking to design their own systems. Okay, I guess one last question. We'll wrap it up with this. There's a few other questions, but I think they may be better addressed via email. So any questions we don't get to now, we will follow up shortly with email answers to those. So I guess the last question here, does OSLO have global optimization capabilities?
Yeah, I mentioned that briefly. It's probably worth showing that a little more seriously. So under optimize here, we have some advanced optimization. Right now, this lens is actually not set up quite right. It has adaptive simulated annealing, which for a while in the field was the only true global optimizer, meaning it just sort of runs and it doesn't matter what point you start from, and there's a real specific definition for that. So that's one method that's not local that you can use. You do have to put bounds on every parameter, and it also has a global explorer, and that's a defined search method. When you run that, it'll generate a number of different possible solutions. And it's been a very effective type of method and one of the IODC winners didn't use Global Explorer in Oslo, but used his own code that has that's based on Ishiki's method and Global Explorer. I believe that was what a key tool that he was using in that. So we definitely have that type of capability.
Okay. Okay, well, since we don't want to run too long, I think we're going to wrap it up there. Again, there's a couple other questions that have come in, but I will forward those along to Dr. Youngworth, and we can address those off air. But once again, I'd like to thank our presenter, Dr. Richard Youngworth. Thank you for an excellent webinar, and we'd also like to thank everyone for attending today. As I mentioned before, we will have this webinar up on our website shortly, probably within the next day or so. So feel free to download it if you'd like to watch it again. And with that, I'm going to say goodbye. And I would like to thank everybody again for attending. And we look forward to seeing you at our next webinar.